is Juan de los Reyes, who came from Ecuador and will speak about a Bilevel optimization approach.
Thank you for the introduction. I would like to start by thanking Claudia and Hasna for inviting me to give a talk here. And it's my first time in Brazil, and I'm loving the visit, actually. My work is on some bilevel optimization approaches for learning in image processing. And what I'm using actually is variational models. So this is the key word on the methodology that we are using for the image processing. And this is a joint work with Carola Schunli from the University of Cambridge and Luca Calatroni, who is right now in the University of Genova, and Chun Cao, who is a postdoc working in Modemat in Quito. So the outline of the talk, I guess you cannot see much of that. I will start by explaining which is the learning approach we are using for processing the images and for learning the parameters in the images. And then I will try to cover some content that I expect to finish within the time that I have. And let me start by explaining the first and the most basic problem in image processing. Yesterday we had a talk of Georgie about the inverse problem setting, and sort of that helps me to explain what I'm using right now. So in case you have a data F, given data, you have to find, or what you want is to find the information, the image U, out of this equation here, which is perturbed by some operator, which is typically a linear or nonlinear forward operator, and some noise, which is given there. So you have an image which is actually perturbed with some noise, maybe with some operator, and what you want is to recover the image U out of that signal that you are giving. You're giving a noisy image, and you want to process that. So typically what you have is an operator which doesn't have an inverse. You cannot invert that operator directly. And what you want is actually to obtain the signal by processing that. This has many possible causes for the ill-posedness, the non-uniqueness, the unstable inversion, the noise that you are having, undersampling, and some other possible causes. So the thing is, like we saw yesterday, you have to regularize using some a priori information of the object that you want to recover in order to get as much information as possible out of the signal that you had at the beginning. So the typical framework is this one. What you have is actually a prior, which is given by a regularizing term. And this prior is containing some information of the image you have, some smoothness of the image that you are wanting to recovering out of the signal you had at the beginning. Then you have some data model, which is given here, and that depends typically, and we are going to see that in a second, from the noise that you have in the image, the type of modeling that you have, the physical process behind that object. And lastly, what you have is to combine these two settings, or these two objects that you have here, both the prior and the data model, with some parameter. It can be a scalar, a positive scalar, it can be a function, but you have to combine in some sort of a multi-objective optimization framework. So let me explain this more in detail. What you have is actually that the model or the results that you are going to recover depends heavily on these both settings that you are using. And what we expect out of this framework, with this framework that I'm going to talk about, is to extract as much information as possible from the data set that you had at the beginning. So you have to recover some image, but you have to extract some information out of it. What difference does it make to consider different settings? For instance, this is the typical image, which is the cameraman. This is the original image. You have a noisy image, and what you want is to recover something as close as possible to this original image out of this image, which is the noisy one. So this, for instance, is a type of prior. This is a type of regularizer. What does it actually is it moves the image to a Sobolev space setting, and you try to recover as much as possible of this image, but you are also using some sort of Laplacian there, and you are also diffusing something in the image. So this is one of the possibilities of the prior, and if you know at the beginning or from the beginning that your image is going to have some smoothness properties, then you may use that. And another possibility is use the so-called total variation regularizer, which is giving also penalization on the gradients, but it's much more sharp in the sense that the image may have discontinuities. Of course, what you want in an image which is black and white is to have discontinuities between one color and the other. So you can recover a much better image out of it with this type of regularizers, and in that sense, you have a whole family of possible regularizers you can choose to obtain a better image. So this is an example of what happens when you increase the regularization. So this is a noisy brain scan, and of course, if you regularize just a bit, what you get is the same or almost the same image that you had at the beginning, so you are not doing anything, right? If you consider much more, or you consider more regularization, what you have is you get the noise, or you get a noise out of the image, but you want to preserve some details of the image. You want to identify some objects in the medical image. But if you regularize even more, then you lose not only the noise. Of course, this image does look much better, but you lose the noise and you lose also details. So this trade-off between the regularizer and the data fidelity is the kind of the key issue in this image processing task. So a part of that, the regularizer is complemented by these data distributions. You have different type of noises which are or may be present in the image. This is a typical Gaussian noise in these MRI images. You have also this positron tomography where you have a Poisson noise type, or you may have, for instance, an impulse type of noise, which is called also the salt and pepper, and you have like white and black spots in the image, which you can process. So these different type of noises, in these three cases, for instance, are the terms are given here, and you have to complement, of course, a nice regularizer or the better possible regularizer with the data model you are considering. So as mentioned before, the key issue is in this setting is to combine both things, the regularizer and the data fidelity for a model, as better as it gets. And of course, there's a bunch of contributions in the past, or there have been a bunch of contributions in the past considering different frameworks to choose actually the best parameter out of the image that you have. And you can see here some contributions in that sense, and let me concentrate on these two items here. And a part of some classical works on Bayesian statistics and some adaptive rules, what we consider in the framework that we are inserted is in some machine learning type of framework when you want to learn from the data something that complements or choose better the parameter that you are looking for. So the complete setting in an abstract way is given like this. So you assume that from the beginning you have a training set of some ground truth and some imperfect data. So you measure and you have some images which you can consider are the actual true ones. And you have also some perturbed noisy images. And this training set is the training set you are going to learn from. I'm going to give you an example in a minute of what I mean with that. Given that you have some sort of combination, some pairs of noisy images and also some exact or true images, what you aim is to consider or to find the image that solves this variational problem, this denoising, this general denoising problem, but you want to get as close as possible to the truth. That's the main idea of the whole setting. So of course, it makes sense if you have a rich and large training set and you want to approach each one of those true images by processing this and choosing the lambda in a better way according to this bi-level optimization setting. So again, you want to optimize in the sense that you want to get as close as possible to the true image, but as a lower level problem, you have again an optimal or an optimization problem where you have to choose the image U bar, which is given here. What's the setting here? So for instance, when you work or in some machines of MRI, what you can get is a better image or a much worse image according to the time of exposure you have. Given, for instance, that you are inserted in a machine as a patient and you are going to be there for 2 days, the image that they can get out of you is very precise. But of course, you don't want to stay 2 days in the machine, right? So if you are a long time in the machine or you use phantoms for that, of course, then you get a much precise image, but you want to have a good image out of exposure time of, I don't know, 10 minutes, 15 minutes. And of course, in that case, what you get in such an amount of time is images or are images corrupted by noise. Of course, if you have a phantom, you have also this true image that you can use. And you can try to learn or try to tune the machine according to this training set that you are having. So this does not only happen with the denoising of images, but also happens with several image processing tasks. One of them is, for instance, when you try to find some objects in the image, and you want to segment the image in some sort of way, then you have to choose several parameters. And from the beginning on, you don't know exactly which one to choose so that you obtain the precise segmentation that you want out of the image. So it's also a setting which is applicable to other image processing tasks and not only to denoising. So there's been a bunch of contributions concerning this type of approach, this bi-level optimization approach. And here I mentioned 3 of the groups who made contributions before, and they were mainly concentrated on the setting of the random Markov random field models. There's also an optimal control approach, which is given by these authors, and there are nice, interesting results in that reference, but there's not much justification from the analytical point of view. And this pioneering work of Eldad Haber and co-workers, which is mainly concerned with optimal design and is in general from the inverse problem setting. And what we did a couple of years ago was try to consider this bi-level setting in a function space framework. Our idea was to consider, and I'm going to come back to that, to consider as much or as close as the physical model that we have in the image. And in parallel at that time, also a work by Kunich and Pock came out where the finite dimensional counterpart was treated and a semi-smooth Newton method was considered for the numerical solution. And afterwards, there were some works concerning different type of a bi-level optimization for image processing action. So again, what we tried to do at that point was to consider a learning problem, but to treat the non-smooth optimization problem in the function space setting. This means, of course, you have to analyze the problem and you get something out of the infinite dimensional setting. You can obtain some Lagrange multipliers and optimality condition. And mainly what we wanted is to derive or to devise a derivative-based method which is mesh independent and with which we can solve or consider the solution of the problem for the bi-level problem. Of course, one of the targets was to consider large image databases because we want to have a large training set you can learn from and determine the type of noise out of the image, which is one of the biggest challenges in this framework. So let me explain you by the TV denoising what we did and we want to continue in this framework. So the typical total variation denoising problem is the following one. Given a signal, which is given by this function f, you want to obtain an image u which is as close as possible to this noisy signal or noisy image. Of course, if you consider just that problem, it's a trivial one and you obtain directly the function f. So you are not doing anything, right? This is the data fidelity model that we are considering in this total variation setting. But if you consider this total variation, what you are doing is trying to preserve constant parts of the signal, right? You can jump, but you can try, or you try to preserve constant parts of the signal. So this is, for instance, a typical processed signal with this framework with the total variation. So you're trying to, this is the perturb, I don't know if you can see that, that gray part, but you try to approach this noisy image, which is given by the gray part, but you are not trying to recover exactly the noisy image. You want to preserve the structure. So it's given like, this is a constant part, then you have a jump. The jump is possible within the total variation framework, but you preserve large parts or large structures which are constant. This is the consequence of the total variation in that setting. So what you have to do, of course, is to choose the lambda accordingly so that you get this result, or you get a good result out of it. Again, so the total variation is given in the general form in this way, and you compensate both with the lambda parameter that you have to choose, and phi is the suitable distance function, which is the data fidelity term. In the previous one is a very easy, which is the Gaussian noise, is the typical one, but you can consider much more general functions. Okay, so our denoising model, what we tried to solve in this setting was to consider different type of noises in the sum here. So you have different parameters, different weights for each type of noise that you are considering, so that you can choose the best combination of possible noise and to get the best processed image out of it. You get the optimal lambda according to the bilevel optimization framework that was written before. The lambdas have to be positive, at least not negative. And concerning the data fidelities, you have several contributions in that sense, and you can consider the Gaussian noise, which is the most classical one. You can consider impulse noise, Poisson noise, and you have different multiplicative type of noise, region noise, Cauchy noise. You have different type of models that you can combine and try to find out which are the best parameters there. So again, our setting is given in this case with this training set of n pairs of images, exact and noisy images. You try to approach the sum in sum, the L2 norm with respect to the true images, and of course in each lower level problem you solve, again, an optimization type of problem. Now, the problem here is challenging in the sense that you have to investigate what you can do with that bilevel optimization problem and try to find out optimality conditions. And a part of the optimality conditions, what you try to do is to compute an adjoint or a gradient to find the numerical solution in an efficient way. So the setting here is quite uncomfortable in the sense that what you are looking for is a bounded variation function, is a space which is not the most comfortable to work with. And what we do in this setting is to consider an additional, for the time being, an additional viscosity term, which should vanish ideally, right? This mu, this weight of this viscosity term should go to 0 and should be as small as possible, but it adds some regularity to the function that you are going to recover. And you can consider the function in a space H1 or H01 in that setting, right? It's a brutal approximation, I know, I'm going back to that. But this is
a finite dimensional optimization. Are you minimizing only over the lambdas?
Yes, for the time being.
So U bar k is given uniquely by the argument of that. Eventually, so U bar is not a variable in the problem.
U bar is determined, yes, it's the solution of the problem. I don't want to say yes because I'm going to the spatially dependent case afterwards. But in principle, you can choose the lambdas as a positive numbers, exactly, or you can also extend to functions, which is what I'm going to present afterwards. But the problem in this setting is, of course, you don't have the U bar. The U bar is determined by the lower level problem. That's what happens. Okay, so this additional viscosity term, this vanishing viscosity term, what allows us is to write down an optimality condition for this type of lower level problem. And with this optimality condition, we can work a little bit more. So what you obtain out of it, of course, the functional is the same, is the L2 functional. But what you obtain out of it is some sort of or what you obtain is a variational inequality of the second kind in this setting. So you have the Laplacian, you have the noise models or the derivative of those objects, of course with the sum in this framework, and you have also the subdifferential of this object that you cannot differentiate actually. This is already a challenging problem. I mean, we are already in the Sobolev space, and that's a good thing. We can work with that, but it's still a challenging problem in the sense that you have here an inclusion or a variational inequality and not an equality directly. So concerning optimality conditions for variational inequalities of the second kind, there have been some works in the past concerning some abstract variational inequalities or the optimal control, and Hasna has also done something concerning that. And the main drawback of these settings were that those were general settings for abstract variational inequalities, and in that sense, the optimality systems that you got were not really adapted to the framework that we were using. So they were a general, non-differentiable term, convex, but you cannot or you could not recover or obtain a sharp optimality system. So what we did more recently is to consider something which is more related to the TV term specifically, not to a general variation inequality setting, but just to the framework that we are using. And there's some sort of revival of interest concerning optimal control of variational inequalities in the sense that you can control different processes like in image processing or viscoplastic fluid flow or other things like that. Which is the main difference concerning the approaches? And it's a very easy idea, but it has an important consequence. And the fact is, what you do is you regularize the subdifferential. And if you regularize the subdifferential, you are again in a framework which is very comfortable for us, which is a PDE, constraint optimization framework. But in that framework, what you have to be careful about is how to regularize this thing. You can regularize in different manners. And you have here, for instance, the subdifferential of the absolute value. You have a Huber type function. And in this case, I don't think you can see, this is the typical C infinity approximation of the function, right? If you consider just the C infinity approximation, which is x over the square root of x squared plus epsilon squared, you have something which never touches the bounds, never touches -1 and +1. And this is something you cannot work with. What is important in this setting is to have something which is closely related to the subdifferential in the sense that it touches the bounds, the -1 and the +1, in a large part of the domain. And that's important. You can use several functions. This is not the only one, but you have to be careful about that. And in that sense, you can consider, you can obtain improved optimality conditions for the optimal control or for the... These UK here? No, these UK are the true images. You know the truth. You know the pairs, FK and UK. FK is the corrupted image, and UK is the true image, the original image. This is the training set. This is the training set. So you want to recover, of course, you want to get as close as possible because you want to determine the parameter which is better suited for that. So yes, in this setting is our images.
Somehow it looks like it's just one dimension. You just draw pictures of just one dimension.
For the purpose of explanation, yes.
So it has to be ported to the two-dimensional set.
The results I'm going to present in a while are two-dimensional, but the signal that I presented was one-dimensional because I wanted just to explain how the total variation was. But the examples are two-dimensional. You mean the linearity here? Yes. The sum?
Consider a more general function, parameterized function.
Yeah, exactly. Thanks for the question. That's exactly what we are looking for right now. So this was the first approach we had to combine the linear models, the fidelities, in a linear way, in a linear fashion. But of course, if you have multiplicative noise, then you have to combine in a different way, and you have to parameterize that. That's exactly. This is for our first approach, what we did in this case, but of course you have some much more extensions in a different setting. But I mean, the combination of these in a nonlinear way, in a nonlinear fashion, if it's differentiable, it's not complicating the structure anymore. So what you have as complication is mainly the presence of the subdifferential. So what we can prove in this setting, actually, after doing the elliptic regularization and after doing the other regularization that we had, is some consistency of the approach. We can prove the existence of an optimal solution, the differentiability of the solution operator of the regularized, of course. And what we can do is also obtain some limit results concerning the regularization, this Huber regularization that was presented in the slide before, and also concerning the elliptic regularization that we did at the beginning. So we have some convergence of the solutions concerning both parameters going to 0. And a part of that, so with this consistency, we can try in the numerics also to set the different parameters in different ways. And if you don't like that, which is also possible, if you don't like to regularize, if you don't like the ellipticity, you can still work with a direct approach, and for that you can hear the talk of David in a while. And there's a price to pay in that sense. And of course, the price to pay is for this type of problem, direct problem, you have to be finite dimensional. And that's the key issue there. So the optimality system for the regularized problem looks like this. And let me explain the four components of this system. So the first is the regularized denoising problem written as optimality condition. So we wrote here, I'm sorry, this type of equation. This is our state equation, right? And this is written again in the optimality system. And this is given here. Then what you have is some adjoint.
Just to be sure, the lambda now depend on gamma, on your regularity.
Yeah, sure. I'm sorry for that. Yes, yes. Then there's a mistake also. This is bar and this is not. So it's the same, right? And those depends on gamma, of course. But we have also some approximation results concerning that as gamma goes to infinity. And a part of the state equation, what you have is an adjoint equation, which is the key object in our setting, because that adjoint allows you to compute the gradient of the cost functional, and with that gradient, of course, you can use optimization methods which are efficient in this setting. And a part of that, you have, in principle, some optimality condition, which is the gradient type of condition, and some complementarity concerning the multipliers, because, of course, the lambda i's are non-negative values. What we could prove, actually, and okay, this is the characterization of the gradient, and what we could prove, actually, is that the optimal parameters are not 0. So are bounded a little bit above of 0, which is helpful for the numerical solution, because in the numerical solution, you don't have to project. You can just look and try to avoid, to overcome, or to go to the negative part, but you don't have to project the algorithm. And projection in the algorithms is a quite slow step. So with this setting, with this regular optimality system, what you can do is going to infinity, right? So you want to recover an optimality condition for the original problem. And for the original problem, what you want is the gamma to go to infinity, because that was the regularization, right? And in that setting, what you can obtain is something a little bit more complicated. You have the image processing problem without the regularization. You have some adjoint also, but you have some extra multipliers which are not regular enough, so you have to write down this kind of optimality condition in this dual space framework. And this is giving you not much information concerning the adjoint, for instance. But you can use the regularized one if you want to compute the numerical solution. Just to mention something concerning this optimality system, this is known, or the type of problem that we are considering can be casted as a generalized mathematical program with equilibrium constraints. And in that setting, within that framework, this optimality system would correspond to a C stationary point of the MPEG for the ones who work in that kind of problems. So we cannot recover much out of it because of the lack of regularity of the multipliers, but we can go back to the regularized one and try to obtain an optimal solution for that. So in this setting, what we used is some numerical solution based on quasi-Newton methods, and we solved the state equation with the Newton type algorithms, the evaluation of the gradient with the adjoint, and we used some basic Armijo line search rule with some curvature verification to obtain the results in this framework. This is just for one image. So we have the original image, the noisy image was just a toy example to test how it works. And I'm going to show you some examples. Here is the Gaussian noise, and what we obtain is a parameter which is close to 3000, and we do the task quite good actually in this setting. If you consider a much more or much noisier image, then the reconstruction is not so good, which can be expected. But still, what we can do is to compute an optimal parameter out of that. This is for Gaussian noise, and this is, for instance, this is an interesting case. This is a mixed Gauss Poisson noise. You combine that linearly, and you can, or you want to reconstruct or to obtain the parameters, and you obtain, this is the original image, this is the noise image, and you obtain this image in the middle. Now you can comment on that and say, okay, this is not the best possible reconstruction. I could do by eye a better reconstruction. I will go on that in a while. But you can recover, you can compute according to your cost functional some optimal parameters for this mixed noise model. If you do with the impulse noise, if you try to solve this kind of problem, then the reconstruction is much better. So this is the noisy image, this is the original one, and you can recover, you can almost remove the whole noise out of the image. And the framework, what I wanted to explain is our cost functional for the time being is a L2 squared cost functional. You want to approach the original image as much as possible in this L2 square norm. This L2 square norm is related to this signal to noise ratio. So what we have here is, for instance, if we reach the minimum, then we reach also the maximum of this signal to noise ratio. And this is, of course, the optimal value that we are recovering. Now, this signal to noise ratio is not precisely or not always the best fidelity measure concerning an image. So you can move and try to consider different type of cost functionals and obtain a better reconstruction. But this is for the L2 square norm, the best possible choice. Now, I'm going to comment something about the dynamic sampling methods. So in principle, what you have is actually not only one image you can compute, you have several images you can learn from. This training set that we had is from K1 to N, and N can be very large, actually. And in this setting, what you do is, of course, you can combine those in this sum. But if you consider this closely, you have to get as close as possible to each true image. But for each reconstructed image, you have to solve a denoising problem. So if you have like 1,000 training pairs, you have to solve a problem which is given by a cost functional and 1,000 denoising problems, 1,000 variational inequalities you have to solve. You have to think a little bit about that. You can try to parallelize and to buy the best machine in the world and try to send each problem to each different processor, or you can adopt a different strategy, which is what we did here in this setting. So again, you have the corrupted images, you have the true images, and you recover the image. And due to the large size, what we can do is actually to consider a number of PDEs that need to be solved as small as possible, but as big as possible so that we don't lose the approximation properties. And that's the key issue here. So what we did is actually, if we sample the PDEs, which are the constraints, we have to think about how to sample the PDEs if we update the sample and how to check the quality of the sample that we are choosing. So in this setting, the important thing here is you consider an initial number of PDEs you want to sample, and while the method proceeds, while the optimization method is going on, you choose if you stay with the same sample or with the same size of the sample, or you increase the size of the sample. This is the main idea here in this framework. So if you consider the cost functional according to this sample you are using, this is just the cost functional, right? I'm sorry for that. What you can consider is a cost functional which is given by or the gradient of the cost functional which is given by the sample, the gradient of the cost functional without the sampling, and what you want is to preserve this inequality here. This inequality here allows you to obtain out of the sample a descent direction for the algorithm. So that's the key element of this setting. Of course, with this inequality, you cannot start or doing something because you cannot compute these objects in a direct way because you cannot solve the whole PDEs and use that. So the idea is to square the term, to square it on both sides, and to get the expected value out of the left-hand side. And if you do that, what you approach is closely the variance of this element, which is given here. And you have to check if you consider this variance of the sample that you are choosing, you can compute this element and try to get or try to preserve the inequality you have in this setting to obtain a descent direction of the algorithm. So if we consider the size, we can keep the size of the sample or we can augment that. And what we can obtain is, for instance, let me just comment these tables. I don't think I have much time. Here are the parameters. This is a single parameter, and this parameter is considering the whole database, and this parameter is considering just the sample of the database. And the difference above between the parameters is given in this right-hand column, and it's around 2%, 3% of the value. And of course, you can see here the difference in the efficiency concerning the PDE solves that each problem has. If we do this batch or we do this sample selection, we can save a lot of computational time concerning the solution of the PDEs that we are having. The same thing happens for two parameters. If we take a look at the cost functional, what we can verify is that the Hessian is very small at the optimal solution. So what we did is actually try to improve that in the sense that the convergence has this type of history. So it oscillates at the beginning, but of course, if we are considered a BFGS algorithm, at the end, we have a local superlinear convergence of that. But we were not satisfied with this oscillation at the beginning. So the first idea that you come up with is to try to improve the approximation of the Hessian. And what we did in this setting was to consider a linearized problem. There's no total variation here. There's no denoising here. But it gives you a flavor of how the Hessian look like. And if you start with that, then you get a much faster convergence for the algorithm by initializing the Hessian in a different type of way. I think I'm over the time right now. Just give you a flavor of what we did in the spatially dependent case, which was commented. So in this setting, what you have to consider is a function which is, it has to have some structure. We consider, for this case, the H1 function, and the parameter is given by a distributed function we have to optimize. And what we try to obtain is the solution of this bilevel in a complete infinite dimensional function space setting in this case. And of course, this causes some problems because the parameter, which is a function now, has to be non-negative, which is involving control constraints in that case. And you have to take care of that numerically also. So we have an optimality system that we solved with a semi-smooth Newton method. We use some domain decomposition algorithm for that. I'm not going into the details. Oh, really? Okay, nice. So what we did is we solved this optimality system. And for this optimality system, we have a complementarity condition. And that's why we needed a semi-smooth Newton algorithm for solving that. Now, if you can imagine, you have coupled state equation, which is a denoising problem. You have a coupled with the adjoint equation, and you have with a third PDE, which is involving the parameters you want to solve. So it's a heavy problem, not very likely that you solve in your personal computer. So what we did in this case was to consider some domain decomposition strategy. So we split the image in different segments of the image and try to combine to solve in each patch of the image, and then to combine the information concerning the parameter or the optimal parameter we solve. So this is the typical domain decomposition sketch. So you consider two overlapped domains and try to figure out the conditions, the transmission conditions between the domains to get a much better result reconstruction. So what we did was to apply this to the setting, to the constraints that we had, and we optimized the choice of the transmission condition where you have different degrees of freedom, and try to solve the whole setting in each patch of the image with a semi-smooth Newton method. So each one is solving a Newton type of algorithm. And just to summarize these results, we obtained, or we could prove that, of course, for each patch, the superlinear convergence of the semi-smooth Newton method is obtained, which is what is expected from the beginning. And the most interesting part is, typically in images, you don't really have an homogeneous noise. So if you have an image with much more light, then you have much noisier image in that part than in other dark parts of the images, for instance. And this is a typical case where in this part you have much more noise than what you have in the other parts of the image. So if you reconstruct and you want to optimize and obtain a better parameter, you have to obtain some sort of function which is modified according to the type of noise that you have. So you regularize much more if you have more noise, and less if you don't have noise at all. And the function is looking like that. So this is the H1 function version, the optimal weight that you obtain with this infinite dimensional setting. And you can reconstruct the image much better with that setting. So let me go to the conclusions of the talk. What we wanted is to present a bilevel, or work on a bilevel optimization framework in function spaces to analyze the whole problem in a better way, and to obtain fast numerical solutions by using optimization-based methods. Of course, the case of the spatial dependent weight is much more complicated because you have to adapt with domain decomposition and semi-smooth Newton algorithms. And the outlook is quite promising. We have tested already with different cost functionals to obtain a better reconstruction. We have used different regularizers for improving the image quality. And we are looking forward actually to some in-painting applications and segmentation applications of this approach to obtain the adequate parameters out of it. And thank you very much for your attention.